అరే అమ్మ నాకు నోట్లో మేడం మేడంకి స్టార్ట్ చేసామనండి. స్టార్ట్ చేసే ముందు డాక్టర్ ఈశ్వర్ సార్ ఆర్ యూ దేర్ అని చెప్పేసి డాక్టర్ ఈశ్వర్రావు అని ఆథర్ అదే పర్సన్ ఉన్నారు కదా, ఒకసారి ఆయన ఉన్నారా లేదో అందులో కన్ఫర్మ్ చేసుకొని స్టార్ట్ చేసేయమని చెప్పండి. ఓకేనా? ఆయన రెస్పాండ్ అయిన వెంటనే స్టార్ట్ చేసేయండి. ఆల్రెడీ ఆయన అందులో ఉన్నారు మేడం, డాక్టర్ ఈశ్వర్రావు అని. ఒకసారి ఆయనకి విష్ చేసేసి సార్ షల్ వి స్టార్ట్ అని చెప్పేసి అప్పుడు స్టార్ట్ చేసేయండి. ఓకేనా? ఓకే ఓకే.
Good afternoon, sir. Sir, are you there, sir? Dr. Nageshwar Rao, sir.
Sir, Ishwar sir, Dr. Ishwar sir, are you there?
Ishwara sir, are you there, sir?
Hello.
Ishwara sir, are you there, sir?
Yes, am I audible?
Yes, sir. Am I audible, sir?
Yes, you're clear.
Okay. Shall we start, sir?
Yeah, please, you can start.
Okay. A warm welcome to everyone. I am Y. Manashwini, working as Assistant Professor at Aditya Institute of Technology and Management, Tekeli. Good afternoon, respected dignitaries, esteemed speakers, faculty members, and participants of the 5-day online faculty development program on quantum computing and machine learning, bridging quantum theory and intelligent systems. It is my privilege to introduce our distinguished speaker for this session, Dr. G.V. Ishwar Rao, an accomplished academician and researcher specializing in quantum machine learning, medical imaging, computer vision, and artificial intelligence. Dr. Rao currently serves as an assistant professor in the Department of Computer Science and Engineering at the Thapar Institute of Engineering and Technology, Punjab. He completed his PhD at Motilal Nehru National Institute of Technology, Allahabad, where he focused on quantum machine learning and its application in medical imaging and computer vision. His research contributions include developing hybrid frameworks for respiratory disease detection using quantum classifiers and classical convolutional neural networks, as well as exploring quantum feature extraction techniques for medical image analysis. These innovative approaches aim to enhance the accuracy and efficiency of diagnostic tools in healthcare. Dr. Rao has published several research papers in reputed journals and conferences, reflecting his commitment to advancing knowledge in his field. His work bridges the gap between quantum computing and practical applications in medical diagnostics, making him a valuable resource for today's session. Please join me in extending a warm welcome to Dr. G.V. Ishwar Rao. We look forward to his insights on the intersection of quantum computing and machine learning in medical applications. Thank you. Over to you, sir.
Yeah, thank you, ma'am. Thank you for your invitation for this particular quantum machine learning and theory workshop.
My pleasure, sir.
Yeah, sure. So let me share my screen. Is it visible, right?
Yes, sir, it is visible.
Yeah. A very good afternoon, one and all. So once again, thanks for the organizing committee and ITM Technical Management for giving this opportunity. And all the participants, welcome to this session. So today's topic is from classical pixel to quantum circuit. So the title, why I just put this title. So actually we are going to discuss the main challenges, the different challenges in the quantum computer vision. Actually computer vision means related to some image processing techniques only. So what are the challenges that are there in the classical images? How can we overcome those challenges with the help of quantum mechanic properties? So simply I can say the title, quantum image processing. So how we can process a simple image. So I'm not going in depth. So I'll usually start with some the overview of quantum mechanic properties. Then we'll see a few examples. How can we correlate these image concept, image processing techniques with respect to quantum. That is the session actually. Today's session that we'll see. A simple, very fundamentals. So first of all, what is the main difference between the classical image processing and this 1 minute. So let me. So yeah. So this is what is the main difference between the classical image processing and quantum image processing. See, in classical, suppose if I ask to if I ask to analyze an image, if I ask to analyze a classical image, you will start from a sequence, like a sequential manner, right? So that is like one instance of time you can analyze only one pixel, so it will take lots of time. At the same time, the feature extraction is also we'll miss many feature values, many feature values, we'll miss those feature values. But in quantum, we can extract all the features at a single instance of time with the help of some quantum mechanic properties, like I think you might heard superposition and entanglement, right? And the beauty of this quantum is like it can evaluate all the image values, image pixels, like parallel simultaneously. So we'll get all the information at simultaneously. So that is the main difference between the classical image and as well as the quantum advantage. So in this session, we'll see how we take the quantum advantage for the image processing to extract the more detailed features. Of course, we'll also in classical image processing we have techniques. We can also extract the features, but it will take some time. At the same time, there are some drawbacks. What are the drawbacks? I'll give some few examples in this session. So that how those actually some gaps are there. Those gaps we can overcome with the help of this quantum advantage. So by applying these quantum mechanic properties. So yeah, this is the main thing. So the main difference is in quantum, everything like the processing of an image or the processing of a pixels is done by the parallel. So the parallel thing. But in and the second thing is we are by using this quantum, we can also extract the more detailed features with the help of some entanglement properties. So that is the main difference between classical image processing and quantum image processing. Next, we need some operations. We need to perform this processing. We need some basic concepts like we usually use in quantum processing, some quantum gates. So actually, basically, there are two types of gates. Like one is quantum gates, single qubit gates, as well as multi-qubit gates. So these are the quantum gates: Hermat gate, rotational gates, CNOT gates. These gates usually we use for processing of an image. So for processing, for the purpose is like for edge detection, as well as the to other like feature extractions. So with the help of entanglement. So this is the another basic preliminary is required to understand the next slides. So quantum gates. Next, before going to actual the concept, so first understand what is the difference between bit and qubit. Usually to process or to store or in a classical, we usually represent either 0 or 1. But in qubit, we usually use qubits, that is ket 0 and ket 1. We usually call it is a ket 0 and ket 1. So this is the representation of qubit. So this is the equivalent 0 state. This is the equivalent state 1. So this is the main difference. So what actually the meaning of ket 0 and ket 1? I'll show it. So this is the main difference. So in classical, everything is represented in 0 or 1. 0 or 1. And for processing, we use the gates like classical logic gates. But here we use quantum gates. Okay, so each and every value in quantum, it will be stored in qubit. So the value is in qubit. Yeah, so this is like, suppose this is the qubit 0. So usually qubit 0. So in quantum computer, usually either 0 or 1 state in a classical or quantum. But the representation is different in quantum. So that is ket 0. So this is ket. And this is ket 1. So this is the representation, right? Yeah. Now, so this is the block sphere. the entire quantum mechanic properties is worked based on these blocks here. So we'll discuss few examples about this blocks here. And the main thing is you have to understand what is the value of qubit actually, qubit 0. So this is nothing but the matrix. Everything is in the matrix form, that is a linear matrix form. So this is 2 by 1 matrix, 2 by 1 matrix form. So 2 by 1 matrix. So what is the meaning of this means? So 0 means the position of 0 is said to be 1. So this is actually the position is 0, 0, 0, comma 0. So that value is said to be 1. The remaining values are said to be zeros. So like this one, suppose is the bit qubit is 1. So ket 1. So here the position is 0 and this position is supposed to be 1. So here the position value is said to be 1. So in this way, actually the qubit values will be right. So based on the positions, the value will be set. So now understand, this is ket 0 means the value, the equivalent matrix value is 1, 0. Ket 1 means 0, 1. So this is actually defined from this block sphere. So this is the actual the background, the main background, and the proof. The property of lemmas are satisfied with respect to this block sphere. This is the quantum block sphere, right? So for this session, you please understand only these two values: how to represent ket 0, how to represent ket 1. So that is just fixed up based on the position of the states, right? Yeah. First, so I discussed already how with respect to our quantum image with image processing, we usually use superposition. So what is superposition? I think you might heard from last 5 days. So superposition is like that allows the evolution, combination of both 0 and 1 states at the same time. So we can evaluate all the state information at the same time. Suppose this is actually there is a proof, Schrodinger's cat, right? So actually in classical this is not possible. So means what? See here the property of cat may be alive or dead. So in classical ultimately we can see only the cat is alive or dead. But in this quantum computation, this superposition concept, this will gives the whole states of properties of cat will get simultaneously at single instance of time. So that is called superposition. Superposition means we'll get all the arbitrary states of the cat position, whether it is live or dead. And other thing is, suppose in classical, whatever the results we are getting, that we believe blindly, whether it is alive or dead. But in quantum computation, we'll conclude or we'll measure the final output based on their amplitude value, based on their probability value. Suppose if I get the result after the measurement, cat is alive 50%, then the other state should be represent 50% which is dead. So like based on this probability will decide the final output. But in classical, this is not possible actually. So whatever the output we are getting, we are just taking as it is. So we are not seeing the other state what is there actually. So this is the actual the property of superposition, the representation of superposition. So I'll show how to represent the superposition. And another example of superposition. So this is like flipping a coin. If I flip a coin, then output is either head or tail. Either head or tail. So but usually in reality, in between there are some arbitrary state. There is a possibility of head, some probability, suppose 50% of probability of head, some 50% of tail. So this information also will be evaluated in the quantum computer. But in classical, we'll see only either head or tail. Head or tail. This is the information. But in classical, we'll get how much probability that will come head, how much probability that will be tail. So this is actually superposition. How to represent in the equation. So this is the equation. Suppose this is the possibility of head, this is the possibility of tail. So this alpha represents probability of tail, the probability of So this is the alpha represents how much probability the coin becomes head, how much probability the coin becomes tail. So this is the representation of superposition. So this is the final superposition state. So what I want to say, so this is the state representation psi. So superposition means the symbol of superposition is represented with psi notation. So this is one state, this is another state. So finally what we understand here, in this superposition state, all the information will be recorded. So everything is recorded, but in classical this is not possible. So we'll get only either alpha or beta, but here we'll get all the arbitrary states. What is the probability to become the final state? So different state, right? So where 0 and 1 are the basis states, alpha and beta are the complex number called probability amplitude. So this is the way to understand the superposition. So this superposition, how we use or how we correlate this property in our image processing, we'll see with an example. Next, another property in quantum entanglement. Entanglement means many meanings will become, but this today's session is related to image processing. So entanglement, I can say how to correlate from one pixel to another pixel to extract the more features, so more patterns, more characteristics. So that is the use of entanglement. Entanglement means we are just combining two different states. We are trying to combine two different states to get more patterns. So that is the use of entanglement. This entanglement definition would be different from area to area. So in cyber security, definition would be different, but the ultimate goal is, so like we'll get some more characteristics with the help of this. We are going to combine some different states. So that is the meaning of entanglement. Okay, so yeah, this is another property, quantum parallelism, that I already discussed. Whatever the computation that is being done in this quantum computation, it is done by completely parallel. So because of superposition, we already discussed. Superposition, every n number of states will be computed in a single instance of time. So that is called quantum parallelism. Yeah, this is the quantum parallelism. In classical, only one state will be computed at a single time. So either 0, 0 will be computed at instance of time, either this state will be computed at one instance of time, or 1, 0 like this. But in classical, all four states can be evaluated in a single, at once. So because of superposition. So this is very important to understanding of quantum computation. Superposition and entanglement, that is very important. So this is called superposition. So due to superposition, that actually parallelism will be happen. Last property, quantum measurement. Till now we have seen two types of mechanic properties. One is superposition, that is, another one is entanglement. So finally our ultimate is, our target is to observe the final output. After whatever you do, whatever you perform with the help of quantum mechanics, but the target is the observation, final output. What is the final output? What we are achieving from the particular processing technique. So that is actually at the last phase with the help of quantum measurement. So once we measure on the superposition and the entanglement state. So now we have two types of states. In our hand, now we have two types of states. One is superposition, then after entanglement state. Now, whatever your use case you perform, then I need to observe the output, final output, what we are achieving. So that is actually the last phase. That is nothing but measurement, right? Suppose in this example, this is a superposition state. Suppose superposition state, of course, how much probability that we have to see final output. What is the head or tail? Suppose 50% head or 50% tail. So that we have to observe. So finally, if it is head, then it is 100%. So this is 100%. If it is 100%, the tail is 0. So this evaluation is also can be recorded in the quantum computation. Suppose if it is 80%, then there is a chance to hit 20%. So 20%. So with this ratio, we'll finalize the output is head only. So depends on the probability. Depends on the probability we are going to record the final output value. And observe one more thing: the alpha square, the probability of alpha square and beta square. So these probability squares of sum of that should be 1. So this, whatever this probability, that should be equivalent to 1. So this is the last phase. Actually, this is the final phase for the final measurement. Yeah. Anyone doubts? So we've just crossed 3 stages. So this is the final measurement. So this is the superposition state. Now this is the again I am telling, we have many measurement techniques that we have, but simply we use this poly Z operator for measurement, simple, basic. So for this session, we have many measurement techniques. So finally, this is the measurement where we will get the final output. We can observe the final output. Okay. Yeah. Next concept, quantum gates. How to process the actual image, the pixel values. So according to our use cases, whatever the application yours, that is completely based on quantum circuits. What are the quantum circuits? Simple. It is like similarly classical gates, but in quantum we have some gates, that is the quantum gates. So what are quantum gates? So we have some quantum gates. Okay. So what are the types of quantum gates? So we have actually single, these are all different types of, these are single qubit gates, and this is the 2 qubit gates. So depends on usage, we are going to use all these gates. So these gates will help in the how to process or how to manipulate your pixel values based on your requirement. So these are ultimately what I want to say, these quantum gates are classified into 2 types, single qubit as well as the 2 qubit gates. Okay, so these are the basic actually, poly gate and these things, and Hadamard gate. So Hadamard gate is used for superposition. Suppose we have states, I want to convert your pixel values into superposition, then this is the gate, Hadamard gate. Right, Hadamard gate, and rotation gates, that we'll see. So now, we have some gates, quantum gates. Now C0 gate is very important for entanglement property. So if I want to entangle, or if I want to combine 2 different types of pixels correlate, so then we must use C0 gate. So this is 2 qubit gate. So how it will work C0 gate? Suppose your input is 0, so there is no change in the target state. There is no change in the target state. If your input is 1, then your target change, the target state will be flipped into 1. Suppose your input state is 1, this is your target state. So this is a control, this is target bit. So if your control bit is 1, your target bit will be flip into reverse. Suppose this is 1, so now it is 0. But if your target bit is 0, there is no, if your control bit is 0, there is no change in the target bit as it is. So this is the working principle of C0 gate, like Hadamard gate. So this is the representation of Hadamard gate. So this is already proved with the help of Bloch sphere. So just understand, if I apply Hadamard gate, the value is 1 by square root of, this is the representation. So lots of proof is there behind this Hadamard gate, how we get these values. That is actually, that is another concept, like linear algebra we have to